Good morning, students. Today we are going to start a new chapter, Work, Energy and Power, and it is chapter 6. Now, all of you know what is work. Now, in lower class, possibly you have got the definition of work like that. Whenever we feel that we are tired or we are wasting energy, then it means that you are doing work. It means if you hold a box on your overhead for 1 hour, definitely you will feel tired. Is not it? It means you are wasting some kind of energy, and as a result, it means you are doing work. Now, in higher class, possibly in class 11, this definition is invalid. It is not define work when we feel that we are wasting energy, and rather there is a specific definition for the work done. And as per the definition, it says that work is said to be done whenever there is a shifting of an object from one place to another place. It's not like that if you hold an object for longer time, when you feel tired, it means you are doing work. That is the definition for lower standard. Now, in our standard, we'll define that work is said to be done whenever there is some kind of displacement. And also, the displacement is not perpendicular to the direction of the force. If it is perpendicular to the direction of the force, then work done is 0. There is more specific definition for the work done. So let me read out what we have written here. Work is said to be done whenever a force is applied on the body and the body moves through a certain distance in the direction of the applied force. Now you see in the figure, we have given a rectangular block. This is some kind of object, and we have applied a force F vector at an angle theta with the horizontal direction. Now when we apply force on this object, what happens? The object moves through a certain distance, as we have defined here S. So force and displacement or force and distance in magnitude is not in the same direction, rather it is an angle theta. Now, as per the definition, what we have written, let me read out. Work is said to be done whenever a force is applied on the body and the body moves through a certain distance in the direction of the applied force. Now you see, force and displacement, these are vector quantity. So if both force and displacement in the same direction, then it is said that work is done. So if we consider specific direction as the displacement direction, then we have to take the component of F vector along the direction of displacement. So force vector along the direction of displacement is your F cos theta, and displacement is your S. So the product is together can be defined as your work done. So in dot product you can write F vector dot S vector. So let me to repeat once again. Work is said to be done whenever a force is applied on the body and the body moves through a certain distance in the direction of the applied force. So here you see, here the displacement is not along the direction of the force, rather it is along the direction of the you see the product, force and displacement, they are not in same direction. So what we have to do, we have to make in the same direction, and then we have to take the product, then that product can be defined as your work done. So you can consider F vector at an angle theta with S, and then product is your F cos theta S. Or if it is S vector, you can take the component of S along the direction of F, then also S cos theta into F. So ultimately it is same. So it is more logical if we consider component of force along the direction of displacement and the displacement magnitude itself, then that product can be defined as your work done. So this is the definition of the work done. So we have to take the component of force vector along the direction of displacement and the displacement itself in magnitude. So the product can be defined as your work done. Now you see F vector and F vector dot S vector. You can write as per the definition of the dot product. Already we have defined dot product. Please check it out. F vector dot S vector is nothing but a work done, and dot product is a scalar product, so you can say work is a scalar quantity. Now if you consider the unit vector, so you can define F vector as your component of I cap, j cap and k cap. So fx I cap plus fy j cap plus fz k cap. S vector also like this, x I cap, y j cap plus z k cap. So x, y, z are the component of S along x, y, and z direction, and fx, fy, fz are the component of F along the direction of the x direction, y direction, and z direction, or along the direction of I cap, j cap, and k cap. So if you take the dot product, so it is nothing but I dot I is your 1 and I dot j is your 0. So ultimately we'll get fx x plus fy y plus fz z. Now dimension for work done is your work, force, and displacement. If you consider cos theta as your 1 and cos theta 1, if theta equal to 0, is not it. It means the force is along the direction of the displacement. So if you take the dimension of F, m1 L1 t minus 2 and L1, it comes out to be your m1 L2 t minus 2. Now regarding the unit in MK system, work done is your work done can be specified as your joule. So 1 joule, as per the definition of the work, again force into displacement. Force is your Newton in MK system and S is your meter. So 1 joule equal to 1 Newton into meter. So work is said to be 1 joule if 1 Newton force is applied and the object moves through a certain distance, which is nothing but is your 1 meter. So 1 erg work is said to be done if 1 dyne force is applied and the object moves through a distance 1 centimeter. Now there is a nature of work, and work may be positive or negative. So we are going to use this equation W equal to F cos theta S or Fs cos theta. If theta value is your 0 to 90 degree, then the work done is positive. Okay, so any value in between 0 and 90 degree or 0 or 90 degree, then the work is said to be positive. And work is negative if theta is greater than 90 degree. Then work done is said to be negative because cos theta goes to negative value. So you see, for example, negative work done is your work done by the frictional force, you can consider. Okay, or you can say work done against the gravitational force. Now let me take one numerical and try to explain. A particle is acted upon by constant force F1 vector equal to 2 I cap minus 3 j cap plus 4 k cap, and F2 equal to minus I cap plus 2 j cap minus 3 k cap. And displaced from the point 2, 1, 0 to the point, you can consider this point as your B, minus 3, 4, minus 4, 2. What will be the total work done? It is asking to define the total work done. You can consider this point as your B. This is your A, 2, 1, 0, and up to the point B, minus 3, minus 4, 2. What will be the total work done by forces? Now here two forces are there. It is acted on the object, so we have to find the resultant of these two forces. Now we have drawn a diagram like this. Suppose the object is at P and you have applied two forces, F1 vector and F2 vector. So resultant force as per the definition of the parallelogram law, so F vector equal to F1 vector plus F2 vector. So F1 vector value is already given, so let me substitute. This one is your F1 vector 2 I cap minus 3 j cap plus 4 k cap, and F2 vector is given minus I cap plus 2 j cap minus 3 k cap. So if we simplify, 2 minus 1, 1 I cap minus 3 plus 2 minus j cap plus 4 minus 3 k cap, and it moves from the position A to B. So in terms of unit vector, this is your 2 I cap plus j cap and minus 3 I cap minus 4 j cap plus 2 k cap as per the coordinate given here. So again, this diagram A and B, we have specified 2 points. So one position vector is your R1 vector, another one is your R2 vector. So if the object moves from A to B, so according to triangle law, R1 vector plus the AB vector equal to R2 vector. So AB vector comes out to be your R2 vector minus R1 vector. So R2 vector is your is given minus 3 I cap plus 4 minus 4 j cap plus 2 k cap, and that is your minus 2 I cap plus j cap. So on simplification, minus 3 I cap minus 2 I cap, so minus 5 I cap, minus 4 j cap minus j cap, so minus 5 j cap, and plus 2 k cap itself plus 2 k cap. So let us consider this is your R vector, say. Now work done W equal to F vector dot R vector. So it is same as this one, only we have used in place of S vector, that is your R vector. You can consider S vector also. So you have to take the dot product of these two. So this one F vector value and this one R vector as per the specification which we have done. F vector is your this one I cap minus j cap plus k cap, and minus 5 I cap minus 5 j cap plus 2 k cap. So if you take the dot product, I cap dot I cap 1, so minus 5, and rest goes to 0. I cap dot j or j cap dot I 0, I cap dot k, that is 0. If it is different unit vector, then dot product is 0 because they are perpendicular to each other. So minus j cap, so it comes out to be your minus 5 minus 1, so plus 5, and I cap at 2, so minus 5 plus 5 goes up, that is your 2. So it's your 2 units because unit is not given here, so it is in terms of unit. Work done is your 2 units. So please go through this sum. It's a very simple, but you have to understand. And from the last chapter, please check out. If you need any numericals to do, please specify, and I will do on the very next day. Okay, no problem at all. So please specify, because so many numericals are there, is not it? So you have to try. If you find any difficulties regarding the exercise numerical, please specify so that I can do it for you. So please go through and put your doubt if you have. Thank you.